Last part of section 3.6, we're working on graphs. And what you're going to see is instead of trying to create a graph from an algebraic function like we've been doing all the way up to this point in chapter 3, now what we're going to do is we're going to try to relate the graphs of f, f prime, and f double prime together. So the function, the derivative, and the second derivative, relate them together and be able to create them based on what we have in front of us. So goals, real simple. I want to try to be able to create the graph of my f prime if I'm given the graph of my f of x. So the f of x in this particular set is going to be the purple graph. So this is my f. Here's another f. If those are my functions, what will the graph of my red function, which is f prime, look like? And then ultimately after that, we're also going to create the graph of f double prime based on the information that we have. So here we've got four functions given to us, 4 f of x's, and we're going to try to go through and make a quick sketch of what their derivatives look like. Well, I'm looking at this first one, and as a rule, that looks like an x squared equation. So let's assume for a second that it is an x squared equation. What would the derivative of an x squared equation be? That derivative would be something x, would be a linear function. So I'm thinking right now, I'm going to create the graph of a linear function, and that linear function is probably going to hit the x-axis once if it's linear. I just need to figure out exactly where. And I don't know if this linear function is going to be have a positive slope on it, a negative slope on it. That's what we got to figure out. So we know that when a function is increasing, its derivative has to be positive. Or when the interval work that we've been doing, we stumbled across, we'd set up our intervals, we'd say derivative is positive, function is increasing. Well, look at here. Here's my function, it's increasing. Well, what would that mean? That must mean that the derivative in that same interval, or that same set of x values, would have to be above the x-axis. Here, my function is decreasing. Well, what would that mean? My function would have to be, or my derivative would have to be negative for that set of x values. So putting all this together, my red function, my derivative function, is going to have to be linear, and it's going to have to be below the x-axis part of the time and above the x-axis part of the time. Well, coincidentally, this purple function is decreasing until it hits this x value and increasing after it leaves that x value. So if I sketch this as my f prime function, derivative is negative when the purple function is going downward. Derivative is positive when the function is going upward. And coincidentally, or not so coincidentally, here is a relative minimum at the exact same x value that derivative hits the x-axis. There's your connection. Look for relative maximums and minimums of your original function to find out where your derivative hits the x-axis. Okay, now let's jump to the second one. So this problem number 2, I see 2 relative extrema, which means the red function is going to hit the x-axis at exactly those same 2 x values. That f function appears to be an x cubed, a cubic function, which means my derivative is probably a quadratic or a square function. So it's probably going to be a parabola. Well, let's think about this. Let's see. Original function is increasing. First derivative would have to be above the x-axis. Original function is decreasing. Original function would have to be below the x-axis. Original function is increasing. Derivative function would have to be above the x-axis, and we said thought we were going to be creating the graph of a parabola. There we go. There's my f prime. Okay, so there's 2 of them. So there's 2. Contrasting that, let's look at this example number 3. Example 3. This time there are no relative extrema. This function appears to me to be increasing the entire time. So if f is increasing the entire time, that means f prime would have to be positive. Again, f appears to be a cubic function, which means my derivative would have to be a quadratic or a parabola function. The only thing this time is this parabola function will not hit the x-axis because there are no relative extrema on that graph. So wherever you choose to put this parabola is going to look like this. Your question, of course, is going to be, how do you know where to put it? Doesn't matter where you put it as long as it's opening upward, doesn't hit the x-axis, And we're going to find out in a second why it has to have a minimum at x equals 0. We'll talk about that in a sec. Okay, and then this number 4. Number 4, I see an absolute value function that's upside down, but I want to look at it one piece at a time. If I look at just this piece, function's increasing and linear. So what will its derivative look like? Its derivative will be positive, and the derivative of a linear function is always a number. Well, what's that number? Well, it depends on what the slope of that purple line is that I just drew. And it looks like that purple line rises 2 for every 1 that it runs. And so my f prime function would be a horizontal line at y equals 2 because the purple line has a slope of 2. And then on the other side, here, linear function, slope of -2. So let's put our derivative function down here at -2, and it's going to be another horizontal line. And again, this would go on forever as those functions go on forever. What about open dot, closed dot? The truth is that red function is not going to be continuous. And for what we know, there wouldn't be a value of the derivative at x equals 1 because the purple function has a sharp turn at x equals 1. Okay, so there's your first derivatives. Now let's repeat, but this time let's figure out second derivative. So second derivative. So my second derivative, let's go back to example 1. Example 1, let's focus in on the red function. Red function is linear. And the function that I drew, it looks like it has a slope of about 2. So let's put a linear function up here at about 2, and let's call it f double prime. Now, depending on the line that you drew, if your line has a different slope than my red one does, then your blue one is going to rise or fall based on what that slope is. Okay? Problem number 2. Problem number 2, there is a parabola function that has one relative minimum. So I'm going to make the second derivative hit the x-axis there. The parabola function is decreasing and then increasing, changing at x equals 1. So that means my blue function or my second derivative function would have to be negative and then positive. So there's my second derivative. Problem number 3, this time red function has one relative minimum. It has one relative minimum, so that means that my second derivative is going to hit the x-axis at x equals 0. And here's something that's kind of interesting. Well, we'll come back to that in a second. So now this parabola is decreased. This red parabola is decreasing and then increasing, which means my second derivative would have to be negative and then positive. There's my f double prime. And last but not least, this one, what's the derivative of a constant? So this red function is constant. So what would be its slope? Its slope would be 0, so it means my second derivative would be at 0. And same thing over here. This red function has a slope of 0, which means my blue function would be at 0. And what happens at x equals 1? Well, since that derivative doesn't exist at x equals 1, then I better make sure that I put a hole in that second derivative graph at x equals 1. Now, before we jump to the next page, I want to make a connection. Little connection here. Look at the blue function. Let's go back to example number 1. Blue function is positive. Let's look at concavity of the purple function. When the blue function is above the x-axis, purple function concave up. Example 2. Blue function below the x-axis, purple function concave down. Blue function above the x-axis, purple function concave up, with an inflection point taking place at the exact value where that second derivative hits the x-axis, which coincidentally is the same place that the red function has a relative min. Example 3. Blue function is below the x-axis. Whoops, supposed to be blue. Blue function is below the x-axis. Red function and the purple function is concave down. Blue function jumps up above the x-axis. Purple function changes to concave up. Blue function hits the x-axis at x equals 0. Purple function has an inflection point. Number 4, blue function is equal to 0 the whole time. Purple function has no concavity. So there's your first side, which is pretty crazy. A lot of stuff going on there. What happens on this second page? The second page we're going to change the rules. The second page, we're going to do the same thing, but this time these are now the graphs of f prime. So these are now your derivative graphs. So I'm going to make purple. Purple is now f prime. So this is f prime, f prime, f prime, f prime. Okay? So I'm going to start with what is probably going to be the easier one for us. Let's call this one the second derivative we're going to make in red. Second derivative is going to be red. Parabola, one relative minimum, red function, linear, working its way up, f double prime. Purple function has two relative extrema. We've already drawn this once. Looks like a cubic. Second derivative function is going to look like a parabola and hit the x-axis twice. This time, purple function decreasing the whole time, which must mean that its derivative is going to be negative the whole time. Purple function, it appears, has a vertical asymptote at x equals, looks like 2. If the purple function doesn't exist at x equals 2, then the derivative of that function can't exist at x equals 2. So what we're going to have here, purple function is decreasing. The derivative of it would have to be negative. Red function is going to look like this also. Purple function decreasing, derivative of it would have to be negative, and none of it can exist. There's got to be a red function. It's got to have a vertical asymptote at x equals 2 also. This last one, we've already done this once. Purple function's increasing with a slope of 2. Red function is going to be a horizontal line at y equals 2. Purple function decreases slope of 2. Red function, horizontal line at y equals negative 2 with no value at x equals 1 because of the sharp turn. So there, we've done second derivative. That's hopefully getting a little easier. Now for the original function. Original function, you've got to reverse your thinking. Original function here. Let's make the original function green this time. Now reverse your thinking. If the derivative hits the x-axis, original function would have to have a max or a min. How do I know if it's a max or a min? Derivative is positive and then negative. Original function would have to go from being increasing to being decreasing. I'm going to randomly put a dot there. There's my relative maximum that goes along with the x value where the first derivative hits the x-axis. Other side, derivative changes from being negative to being positive at this x value, which means my original function would have to have a max or a min. In this case, it'll be a min because derivative changes from negative to positive. How do you know how high to put the min or how high to put the max or how low to put the min? Doesn't matter as long as they're a max or a min. These graphs are going to look a little different. You've actually got some freedom. Okay, example 6. Let's do the same thing. So derivative hits the x-axis here, changes from being negative to being positive, which means your function is going to have a relative minimum. Derivative is positive the rest of the way, which means function would have to be increasing the rest of the way. Second derivative, let's talk about concavity. Second derivative is positive until it hits this x value, then negative. So my function is going to be concave up, which makes sense for what I have here, until it hits this x value where the second derivative changes signs. Have to be concave down until we hit the other place that the second derivative hits the x-axis. Then it would have to change again to being concave up to finish off the function. So there's my f in both cases. This example 2 is a little confusing. Relative min, inflection point right here because the second derivative changes from being negative to being positive at that x value. So that green one will probably will be a good place for us to talk sometime soon. And then this example 7, which is going to be confusing again. If my purple function is my derivative, if that derivative is negative, my function has to be decreasing and it won't exist at x equals 2. My derivative is positive. My function would have to be increasing And if we're looking at concavity, second derivative is negative, function's concave down. Second derivative is negative, function's concave down. None of these functions exist at x equals 2. And last but not least, number 8, problem number 8. Okay, so working backwards, let's see this derivative. Let's split this into two pieces. I want to work with this part of the f prime first. If that's my f prime, derivative changes from negative to positive, function would have a relative minimum. Second part. Oh, and wait a minute, and if we look at the red function's positive, green function concave up. Red function negative, purple function decreasing, original function concave down with a relative maximum at that x value, relative max right about in here someplace. Now here's the thing. Looking at the purple function is continuous everywhere. It exists everywhere, which means the derivative exists at every place. The purple function exists at every x value, which means the green function has to be continuous at every x value. We had a theorem not long ago that said if a function is differentiable, it's also continuous. If a function is differentiable at an x value, it's also continuous at that x value. This purple graph exists everywhere, which means my original function would be continuous everywhere. Pretty abstract day today.